Hello, I'm going to be doing chapter 2, problem 48. So we have a volcano that launches a boulder into the air at an initial velocity of 40 meters per second. Part A asks, at what time after being ejected is the boulder moving at 20 meters per second? So we want to go from 40 meters per second to 20 meters per second. So just a few equations that might be helpful throughout this exercise. The change in velocity is equal to the acceleration times the change in time. Acceleration, change in velocity over change in time. And these are all basically the same equation, just worked in different directions. The change in time equals change in velocity over acceleration. So we want to know how long it takes to get to 20 meters per second. So to find that, let's plug it into this equation here. Find the change in time, which is going to be the change in velocity. And the change in velocity, so the difference in velocity here was 20 meters per second. Well, negative 20 meters per second as we go in this direction. So negative 20 meters per second over our acceleration, which the only acceleration acting on this is gravity. So negative 9.8 meters per second squared. And when you cancel out the units here, you actually end up with just seconds, which is perfect. So our change in time, when you do that simple equation here, is 2.04 seconds. So that's how long it takes to go from 40 meters per second in the upward direction to 20 meters per second in the upward direction, and that's the answer to A. Part B asks, at what time is it moving 20 meters per second downward? That's basically the exact same question, just with a different parameter. Now, the only difference is going to be what is our change in velocity. To go from 40 to negative 20, rather than it being a change of 20, it's actually a change of 60 in the downward direction. So our delta t equals negative 60 meters per second over gravity, which is our acceleration. And that comes out to 6.12 seconds. So that's how long it takes to go from 40 meters per second upward to 20 meters per second downward. And then part C, what is the displacement of the boulder from its initial position 0? Or sorry, when is the displacement of the boulder from its initial position 0? So basically, when does it come back to its initial position? That's also crazy similar to what we've already done. Basically, we want to know when. So since the only acceleration in the whole system is gravity, it'll take the same amount of time to reach velocity 0 as it does to get back from, or it'll go the same amount of distance to get from position 0 at 40 meters per second to velocity 0 and then back down to position 0. So all we really need to know is when it gets from 40 meters per second to 0 meters per second, and then we'll just multiply that that change in time times 2, because the amount of time to get to the top is the same as the amount of time to get to the bottom. So plug them in, negative 40 40 meters per second over negative 9.8 meters per second squared. That will get you 4.08 seconds. And that's just how long it takes to get to the top. So you multiply that by 2, you get 8.16 seconds for it to get back to where the displacement is 0. Let's see. And then part D, when is the velocity of the boulder 0? That's already found in our equation C, because when does the velocity equal 0? It's right here. So part D equals 4.08 seconds. And then part E, what are the magnitude and direction of the acceleration while the boulder is moving upward, moving downward at the highest point? So it asks, what is the magnitude and direction of the acceleration at each different point in this graph? But the thing is the acceleration is constant in the whole system. So for all of the different parts of part E, we can say the magnitude and direction are always, for every single one of those answers, it's in the downward direction of 9.8 meters per second squared, because that's the value of gravity. Or you could say it's 1 g. That's for all of part